Hi, welcome back to General Chemistry 1. I'm Dr. Feng Xu, and today we're going to talk about molecular orbital theory. This is the last topic in Chapter 11 and also the last topic in General Chemistry 1. This topic will only be included in the homework, but will not be included in the exam, just to let you know. Okay, so what is molecular orbital theory? Molecular orbital theory pictures a molecule as a collection of nuclei with orbitals that extend over the whole molecule and are occupied by delocalized electrons. So in other words, it's a similar concept of orbital hybridization. Instead of using orbital hybridization of only one atom, we are kind of mixed all the orbitals from the atoms together within a molecule and give a set of new orbitals that belongs to this molecule. And all the electrons from each atom were floating around these orbitals within the molecule, and then filling the orbitals of the molecules. And how to generate these molecular orbitals? So they are formed by adding or subtracting the wave functions of atomic orbitals. So wave functions is a function to describe atomic orbitals. You don't need to know how to solve that in this General Chemistry 1 class. Okay, so that leads to a formation of bonding molecular orbitals and anti-bonding molecular orbitals, respectively. Based on the wording, electrons in the bonding orbitals contribute to a bond formation. Electrons in anti-bonding orbitals does not contribute to a bond formation, and that can make a molecule unstable. So we'll talk about that later. Just to show you how to generate a molecular orbital. So again, if we have the two peaks, each of the peak corresponding to a wave function of atomic orbitals, adding them together, you can have this red curve with two peaks. This is adding atomic orbitals together to form a molecular orbital. Instead, we can also minus them and have this new shape of the red curve. That's by adding on the left and subtracting on the right to form the molecular orbitals. So we will start with a simple case, the molecular orbital of homonuclear diatomic molecules. Homonucleus means these two atoms in the molecules are the same. Diatomic molecules means there are only two atoms in the molecule. So for example, hydrogen. Hydrogen has an 1s orbital. It only has one s orbital that is occupied by electrons. So it has one s orbital in each of them. So on the left and the right side, we have the atomic orbital of hydrogen. When we do the adding or subtracting of these two atomic orbitals, we're going to make two molecular orbitals, right? So the number of orbitals does not change before and after. So we can make it two orbitals. One is bonding orbital, one is anti-bonding molecular orbital. And then we start to fill in the electrons from the lower energy to high energy of the molecular orbitals. Then these, two electrons, valence electrons of hydrogen filling the sigma 1s orbital, the name of newly formed bonding molecular orbital of hydrogen molecule. Okay, so the central part is called molecular orbital. If we have other, elements, diatomic elements in the second period, we also can have oxygen, fluorine, and neon, and also boron, carbon, and nitrogen. So these two need to pay attention when they form this molecular orbital. 2s and 2s mixed up together to form two molecular orbitals, and also 2p orbitals can mix together to form also in total 6 molecular orbitals. Like 3 of them is a bonding orbital, sigma 2p, pi 2p, and 3 of them are anti-bonding orbital, pi 2p, sigma 2p. But for the anti-bonding orbital, we put a star on the right of this pi, on the right of the name of the molecular orbital. Okay, but you need to pay attention that the sequence of this molecular orbital are different for different homonuclear diatomic molecules. Okay, for the sigma 2s, it's always sigma 2s, it's lower energy, and then anti-bonding of sigma star 2s is higher energy. But then for the oxygen, fluorine, and neon, Then we have the sigma 2p, pi 2p, 2 pi 2p orbitals actually here. And then the antibonding pi star 2p, and then finally the sigma star 2p. But for boron, carbon, and nitrogen, the diatomic molecules, the 2p orbital, when they mix it up, we have pi 2p as a more stable binding molecular orbital than sigma 2p, then pi star 2p, and then sigma star 2p. So the sequence of these are different. And you do need to know the energy level of all molecular orbitals in each case of the period 2 atoms from low to high level. Okay, so how do we fill in atoms in the molecular orbitals? So, and these are the one of the common questions asked regarding molecular orbitals of homonuclear diatomic molecules. So first, get the molecular diagram from low energy to high energy. So there's a summary of that in the textbook with boron, carbon, and nitrogen, and also oxygen, fluorine, and neon. The sequence of this molecular orbital are listed on the left and on the right correspondingly to this table. Then, so you need to remember the sequence. And then filling electrons in each of these orbitals and use valence electron configuration. It's almost the same as electron configuration we had before for atoms. So you need to first write the name of molecular orbital, put that in parentheses. In the right superscript, indicate how many valence electrons are there in that specific orbital. And then for the molecular orbitals, we start with the orbital with the lowest energy and all the way to the highest energy, if it's occupied by an electron. Okay, so we can count the number of valence electrons of the molecule and start to fill in the electrons from the lower energy to higher energy sequence of molecular orbitals. In case you ask to fill in molecular orbital of heteronuclear diatomic molecules, the ideas are the same, but just need to find out the sequence of this molecular orbital for the heteronuclear diatomic molecules. We had a few examples in the textbook, and if you're interested, you can try to check them out by yourself. All right, and finally, the last slide is about calculate the bond order of homonuclear diatomic species. Since we have the bonding molecular orbital and antibonding molecular orbital, we can use that to know. So first know how many electrons are there in the bonding and antibonding orbitals, and then we can use that to calculate the bond order. The formula to count bond order is bond order equals to half of number of electrons in bonding molecular orbitals minus the number of electrons in antibonding molecular orbitals. Okay, so first do the subtraction and divide that by half. If the bond order is larger than 0, that means the molecule is more stable than the separated atoms, so the molecule will form. If the bonding order equals to 0, that means the molecule is as stable as the separated atoms, so it will not form. So it does not have enough driving force to form a molecule. And usually you should not have a bonding order smaller than 0. That just means you probably did some wrong in your calculation. In general, the higher the bond order, the more stable the molecule is. Let's take a look at the question. Using the molecular theory, what is the bond order of lithium-2 and beryllium-2? Okay, for lithium, each lithium has 1s valence electrons. So each of them has 2s, the atomic orbitals. Mix them together to form the molecular orbital. We have sigma 2s and sigma star 2s. Because we only have 2 valence electrons, we're filling all the valence electrons in the sigma 2s, the bonding molecular orbital. So the bond order for lithium-2 is using the 2 electrons in the bonding orbital minus 0 in the anti-bonding orbital and divide that number by 2, the bond order is 1. But for beryllium diatomic molecules, it starts with the 2s orbitals completely filled by a pair of electrons. So when we form the molecular orbital sigma 2s and sigma star 2s, all of these 2 molecular orbitals will be completely filled by each of them by a pair of electrons. So the bond order for beryllium 2 molecule is 2 in the electrons in the bonding orbital minus the 2 electrons in the anti-bonding molecular orbital, use a number divided by 2, that is 0. That means for lithium 2, there's a tendency to form this lithium 2 molecule, but from atoms. But for beryllium 2, there's no tendency, there's no driving force. So to form this beryllium 2 molecule from the 2 atoms. So the Be2 molecule may not form from single atoms. Okay, so this is the end of this video, and thank you for watching all the videos here in General Chemistry 1. Good luck in reviewing all the materials and wish you success in this course. Bye.